Hi, this is a video on thermal expansion, and I'm following the order of topics in Young and Freedman's University Physics. So if you've been around for a little while, you know that when things get hot, they tend to expand, and when things get cold, they tend to contract. This is why in this winter, you'll notice in the north there are bridges they have little gaps, metal things next to each other with a little gap in between. This is because in the summer, when it gets hot, these will expand and fit nicely, and then in the winter they pull apart. Now, if you didn't do that, then in the winter it would crack. But because they have the gap there, in the summer it expands to close, and then in the winter it just pulls a little part with a gap. There's a video, I mean not a video, there's a picture of a military plane in this section of the chapter, and it's talking about how these planes actually leak their fuel when they're on the ground. But then when they take off and they hit supersonic speeds, they heat up, and this causes the tanks that hold the fuel to contract and close up. The wings close up. It's kind of a strange thing. But over time, people have come to accommodate these sorts of circumstances so that you don't have to constantly be replacing the roads or the bridges, at least for that reason. Well, let's start by talking about linear expansion. Here we're talking about mostly things that can be conceptualized as two-dimensional. Everything's three-dimensional, but there's some approximation in these areas. So basically, what it's the case that the change in length is roughly directly proportional to the change in temperature for smallish temperature changes. So if we're talking about less than 100 degrees Celsius temperature change, it's roughly going to be a line, directly proportional between the change in length and the change in temperature. Okay, that's one data point. Then they've also discovered that the change in length is directly proportional to the starting length. And so if you have twice as long of something to start off with, then you're going to have twice as much of a change in the length as the temperature changes. And so the neat thing about physics is if you get a feel for how they came up with these equations. I know that delta L is directly proportional to delta T, and I know that delta L is directly proportional to the initial L. All we need is to stick a constant in there, and we can go into an equation. And so if I stick this alpha in here, a constant, we're calling this a coefficient of linear expansion. If I take this, so delta L is proportional to delta T, and delta L is proportional to the initial L. So all I need to do is put in that constant of proportionality, and ta-da! I have an equation that works for smaller temperature changes, less than 100 degrees Celsius temperature changes. Now, the units are 1 over Kelvin or 1 over Celsius degrees, and or K to the minus 1. The space of a Kelvin or the space of a Celsius degree is the same, so it can be either one, as long as you're consistent in your math. Okay, so this is true, like I said, if delta T is not too large. Here's an interesting sidebar. In this chapter, they talk about what happens. Let's say that you've got a metal washer with a hole in the middle, and you heat it up. What's going to happen? Well, I think we can predict nicely that the outer, it's going to expand like this on the outside. But I was wondering whether you might initially think, well, if the inside expands, maybe the hole will get smaller. Nope. As it turns out, that if you heat up something with a hole in it, the hole will get bigger. And if you cool down something with a hole in it, the hole will get smaller. They explain why this is. It has to do with the way molecules work, and they give a diagram of a molecule. It is easier to expand a molecule, apparently, than it is to compress a molecule. And so the net expansion is going to be outward for the hole rather than inward. And so, who knew? A hole gets bigger when you heat it up something. Okay. The same principles for linear expansion also work for volume expansion. Here we're talking about three-dimensional things like a cube or a lake is three-dimensional too. And the formula turns out to be very, very similar. So remember, the other formula was delta L equals alpha times L initial delta T. Well, we substitute in volume. The change in volume, delta V, equals another constant, beta, times the initial volume times delta T. We need a different constant for this, but as it turns out, for solids, this beta is called the coefficient of volume expansion. Okay, fine. But in solids, this beta, and they derive this using calculus in the textbook, beta turns out to be 3 alpha under these circumstances, for low density things, if I remember correctly. In many substances, beta decreases, it gets smaller at low temperatures. Okay, so let's move on to water expansion. Water is a unique thing among substances. Water actually, water, let's say you have 100-degree almost boiling water, 99-degree almost boiling water. And as you cool it down, its density, it's going to decrease, and its volume is going to decrease. Now, normally that would go on forever for other substances, but water uniquely, when you get to 4 degrees Celsius, it actually increases in volume in between 4 degrees Celsius and 0 degrees Celsius. And so you've got that little place where the density hits a maximum. So beta is negative in this range. The greatest density of water is at 4 degrees Celsius. Now, this actually has made life possible. We would not be having this conversation right now if this was not true of water. Now, I'm a theist, so I might say, ta-da, God designed the universe this way so that we could have life here. A non-theist might say, it's the anthropic principle. We wouldn't be having this discussion if coincidentally it hadn't worked out this way. Okay, fine. I'll be a theist. It's also, someone might say, well, maybe life could have evolved in some other way that doesn't involve water. Well, maybe one day we'll find out whether there's other kinds of life out there. But anyway, these properties are why lakes don't freeze from the bottom up. If a lake was made of natural gas, it would freeze from the bottom up. But because of this characteristic of water, it freezes from the top down, which allows for fish and all kinds of sea life to live below the surface of the water. And so what happens is, at the top of the water, let's say you've got ice at the top of the water. Well, the water right below it is going to be, around 0 degrees, say in that 0 to 4 degree range. Well, the density of the water just under the ice then, because it's in that 0 to 4 degrees range, the density is going to be greater, and therefore that water is going to drop, and the ice is going to be at the top. And so this allows the ice to be at the top because the water right underneath it in that 0 to 4 range is denser, and therefore it falls down further. So this is why ice floats, because the density of the ice is actually less than the density of the water underneath the ice. Okay, the final, this is a long section, by the way. Thermal stress. So let's say that something retains its shape for a while. Eventually it might crack or whatever. But let's say that something retains its shape while it's being heated or cooled. Well, obviously you must have competing forces at work there. What kind of stress does a temperature change put on an object that managed to keep the same shape for a little while? Well, obviously if it's heating up, then the thermal stress that's wanting to expand it must be counteracted by some kind of a compressive stress that's holding it in. Or if you're freezing it and it wants to compress from the thermal stress, then there must be some kind of a tensile stress that's keeping it from doing that. So the last section talks a little bit about thermal stress. So you remember Young's modulus from a long time ago? So Young's modulus has to do with the stress over strain, of some object. And so the Young's modulus Y equals the force per area divided by the change in length divided by the initial length. That's Young's modulus, and it has to do with tension stress. And so we can rearrange, do a little algebra, and we end up with the change in length divided by the initial length as it relates to tension equals the force per area times the Young's modulus. Okay, I just rearranged those. So now we know from this section that in terms of thermal stress, the change in length equals alpha delta T. Here I've just taken that initial linear formula and rearranged the elements around. Well, I see an equation coming on. If it's maintaining its shape, then whatever the thermal wants it to do has to be equaling a tension that's resisting it. And so we can equate these two together and say that this equals this in the opposite direction. And we can solve for the force per area and basically come to the conclusion that the thermal stress, force per area, equals the negative of Young's modulus times this coefficient of linear expansion times the change in temperature. And there you have it. That's this section. Quite a long section, but we made it.